Welcome to the EPG Pathashala program of the UGC lecture series in computer science on the subject compiler design. So far we have discussed basically the lexical analysis phase of the compiler. Now we will move on to the second phase of the compiler, which is the syntax analysis. So in that this module is going to discuss about the top down parser, the pre-processing that is required for the top down parser. The learning objectives of this module are to design a top down parser, to understand the prerequisite for a LL1 parser, which is actually a type of top down parser, to learn to left factor and eliminate left recursion from a grammar. So the left factoring, the left recursion elimination are these two prerequisites that has to be met for a LL1 parser. The keywords that we are going to discuss here are the LL1 parser, left recursion elimination and left factoring. So let us just briefly go through the introduction for a parser before we actually discuss the pre-processing required for LL1 parser. Parser is typically integrated with the lexical phase of the compiler. So if you remember the first module which we talked about, we said that there is a get and give command between the lexer and the parser which is happening. The lexer issues a token whenever a parser is going to ask it for a token. So this that is why we say the parser is typically integrated with the lexical phase of the compiler. And the parser can be of two varieties, one is top down parser, other one is bottom up parser. The functions of the parser are, it is to validate the syntax of the programming language. So given any programming construct, say for example a declaration or a for loop or a if then construct or a while loop or whatever it is, whether this particular loop construct or whether this particular construct obeys the syntax of the programming language need to be first checked before it actually gets converted to code. So that is the primary function of the parser, and it also, in the case of an error, it points out the errors in the statements. Okay. So this is just pointing out the errors, and in order to proceed with the next phase of the compilation, the parser basically does an error recovery. Okay. It is not going to correct the error, it is just going to recover from the errors in order to proceed for it to the next phase of the compilation. So the primary function of the parser is to just validate the syntax of the programming language. So this is what is the role of the parser. Given a source code to the scanner is your lexical phase, which is otherwise called as the lexer also. It issues tokens and the parser will pass this, checks whether the tokens are in sequence and gives it to the next phase of the compiler. So this is from the Aho Sethi Ullman textbook, which says the lexical analyzer basically issues a token along with its token value whenever the parser asks for gives a get next token command. In both the phases of the compiler, integrates with the symbol table. Remember, the symbol table gets created right in the first phase of the compiler itself. Whenever it looks for some statements, whenever it encounters a particular statement, it basically populates the symbol table. So the symbol table gets populated right in the first phase of the compiler. The parser also uses this symbol table and then tries to check whether the syntax of the every construct, every statement is obeyed or not, and if it is correct, it is going to just construct what is called as a parse tree or a derivation tree, or otherwise called a syntax tree, which is used by the next phase of the compiler, which is your semantic given to the intermediate representation. The semantic phase also works on the constructed parse tree, which the parser basically constructs. So the parser and the lexer talk to each other with reference to a get next token command, and a token is being issued by the lexer. So the general types of parsers, we have basically three types of parsers. The first one is called as the universal parser. The two examples are the early parser and the other one is the CYK parser, Kokke Younger Kasami parser. Now these two parsers are basically for processing natural language, typically it is used. The other one is top down parser and the third one is bottom up parsers. So the universal parsers, either the CYK parser or the early parser, it can basically parse any grammar given to it and typically used in NLP, but it is too inefficient in compilers. It is you cannot look at the context free aspect of that is not processed by the CYK parser or the early parser. So, therefore, this parser is not basically followed in compilers. What we go in for is a top down parser. The top down parser, it constructs the parse tree from top to bottom. Okay, we will see on how to construct the parse tree etc. as we move on here. Once it can construct a parse tree correctly from top to bottom, where the root happens to be the start symbol of a particular grammar and the children will be the leaves. Okay. So, if the tree is constructed correctly, then we say that the syntax is correct for the particular statement, else we say that the syntax is going to be incorrect. And it can be two types of top down parsers. One is a recursive descent parser. This requires backtracking. The other one is called as the LL parsers, which requires no backtracking. This is the second variety of parsers. The third, before on the third variety, let us just consider this grammar. S produces CAD, okay, and A produces AB or A. Now, this is called as a context free grammar, where it has got productions. Productions will basically have a left hand side and right hand side, and typically the symbol on the left hand side is called as the non-terminal, and the symbols on the RHS, the right hand side, can be a combination of terminals and non-terminals. Terminals are the ones which is going to constitute your string. Now, consider this grammar. It has got two productions. S produces C capital A small d, A produces AB or A. Now, typically the small letters are basically used to represent input symbols, which is called as the terminals, and the capital symbols are typically used to represent non-terminals. Non-terminals means it can replace, or whenever I encounter non-terminal, it could be replaced with the RHS of the production. Any one production can be used for its replacement to derive a particular string. Consider this example. Let the input be CAD, let the input string be CAD. Now, this is how expand A using the first alternative, A produces AB, and so I have the start symbol S, and then I have CAD as its production, because S has got only one production. Now, A could be replaced with AB, okay, but what I want the string as CAD. So, I will start with this CAD, and if I can replace this A with a small a. Now, how is the string looked upon? The string is looked upon by visiting all the leaf nodes from left to right. So, CAD. So, this is my string. This is called as the parse tree or the derivation tree, and the process is called as deriving a string. Okay. Now, if I could derive a string from the start symbol, I will call that this string belongs to this grammar. Okay. So, this is called as top down parsing, where I will start with the root and I will start building the tree. If I am not able to see that string, I go back and then try an alternate production. So, this process is basically backtracking. So, a recursive descent parser, okay, has backtracking problem, where if I am not able to proceed further, I will go back to the previous level and then try an alternate production for checking whether the string belongs to it or not. Now, this has to be avoided. Backtracking typically is avoided, and that is why we have a variation which is called as LL1 parser, okay, or LL of K parser in general. Now, the next is bottom up parser, where you start from the bottom and work up to the root for parsing a string. So, what you do is, rather than trying to get a string derived, we will look at the string, okay, and then try to replace the string with the LHS of the production and then try to derive to the root. If I could get the start symbol, then I know that my parsing is correct, else I say that my parsing is going to be incorrect. So, LR parsers are typically bottom up parsers. There are other variations of LR bottom up parsers also, which is called as a shift reduce parser, operator precedence parser, etc. Now, this is my string. So, I will start from here, okay, I will start from CAD. Now, this A could be replaced with a capital A, okay, this A could be replaced by a capital A, and together C, this A and this D could be replaced with S. So, from CAD I am able to go till S, therefore, I say that the string is going to be correct. So, top down parsers start deriving the string in a top down fashion, where it starts from the root happens to be the start symbol, and it starts deriving the string by replacing the root with one of its productions and then trying to apply one production after another production. So, there is a problem called as backtracking in this scenario. LL1 parsers typically avoids backtracking by doing some pre-processing to your grammar. Okay. On the other hand, bottom up parsers looks from the string, okay, and start applying the RHS, the production, with the LHS, and then tries to build the parse tree from bottom to top. Thereby, if the top, the root happens to be your start symbol, you say that it is correct parsing, else you say it is going to be incorrect parsing. Both the top down and bottom up parsers parse the string based on a property called as viable prefix. Viable prefix in the sense that given a particular grammar construct, if a particular prefix of a string can be validated for correctness or incorrectness. If I say that the prefix itself is going to be incorrect, then I will stop my parsing and I will start recovering and then go to the next character or next string, okay, go to next character, or I will keep on recovering to look for the correct prefix that matches a particular grammar. So, basically what happens is, viable prefix is nothing but, given a grammar, you will know what possibilities are there for a string to start with. So, both the top down parser and bottom up parser parse the string based on this particular viable prefix property. Now, this property states that, formally stating it, before the string is fully processed, if there is an error, the parser will identify it and recovers. Now, before we move on, let us just do a quick recap on context free grammar. I have already told you about grammar here. All programming language constructs are defined using what is called as context free grammar. For example, E produces, this symbol here, this arrow here indicates produces, meaning that LHS can be replaced with any one of these combination of symbols. So, I have here E produces, E plus E, E star E, or parenthesis E close parenthesis, or ID, meaning that this is an expression grammar, that is, this is an grammar for generating or for checking whether an arithmetic expression is correct or incorrect. Okay. So, this grammar has a language of an arithmetic expression, to formally state it. It involves the operators plus, star, open parenthesis, close parenthesis, and ID. Now, what is the production here means? It means that the LHS non-terminal could be substituted with the RHS E plus E, or wherever I see E, I could replace this with any one of these 4 productions. Okay. So, that is what basically it means. Now, formally defining CFG, context free grammar, consists of variables, terminals, productions, and start symbol, where variables are otherwise called as non-terminals, and S is a special symbol which belongs to the variable set, and productions will have an LHS and an RHS, where the LHS will typically be a non-terminal, RHS will be a combination of terminals and non-terminals. So, for example, in this expression grammar, whatever we have seen just now, the start symbol happens to be E, okay, and the terminals happens to be plus, star, open parenthesis, close parenthesis, and ID, and there is only one non-terminal here, and that is going to be the start symbol itself. So, this is the formal definition of context free grammar. Variables are otherwise called as non-terminals. Now, let us take one more example from a programming language point of view. Now, statement, STMT basically means statement. Statement produces if expression, then statement, else statement. Statement can also produce if expression, then statement. Statement can also be a single A. Now, this A basically refers to any other statement, any other assignment statement, or a simple declaration, or a simple return, or whatever it is. Anything could be called as this, could be represented with this particular A. Now, E produces B. E produces B in the sense that there is one more non-terminal available here, which is E. Now, E refers to expression. This is a if-then construct. We all of us know that. So, if-then construct, what will happen if there is a condition, you will check for the condition, and if this condition is met, then you will evaluate the body of the if statement, else you will evaluate, if the condition is not met, you will evaluate the body of the else statement. That is what this particular first production basically refers to. The second one refers to if expression, then statement, meaning that there is no else part. If the condition is met, you will evaluate the statement, else you will not even look into what this statement is. So, this expression can be anything, but what happens, this expression finally evaluates to a true or a false value. Therefore, we say here E produces B. Okay, we just simply say E produces B here. Here statement STMT and E are non-terminals. If, then, else, A, comma B are going to be terminals. The start symbol happens to be statement, okay, and the productions are basically given here. Now we know that the terminals are typically are denoted using small case letters A, B, C, etc. This is specific terminals like 0, 1, ID, plus, all specific terminals. Non-terminals are typically given with A, B, C, capital A, B, C. Here I just gave an example statement, STMT is also a non-terminal. Grammar symbols are X, Y, Z belongs to variables union terminals. So generally if I say symbol, it consists of variables and terminals together. And strings of terminals, so if I have a string U, V, W, X, Y, Z, strings will belong to T star. T star means combination of T's, combination of the terminals. And strings of grammar symbol, which is a combination of terminals and non-terminals, that is denoted by the Greek symbols alpha, beta, gamma, etc. Now derivation. Now what happens here is terminology called as one-step derivation, meaning that alpha, A, beta. Now this alpha is a combination of terminals and non-terminals, beta is also a combination of terminals and non-terminals. This will derive alpha, gamma, beta if there is a production A produces gamma in your grammar. This is called as derivation. So this is how you derive a particular string in your grammar. In addition, we also talk about what is called as left derivation as well as right derivation. Left derivation means the leftmost non-terminal is replaced before replacing any non-terminal to its right, okay. That is leftmost derivation. Rightmost derivation is just the reverse. If the rightmost non-terminal is replaced before replacing any non-terminals to its left, okay. Now this derivation can also be a transitive closure derivation, that is 0 or more steps. I can indicate star and or I can indicate a plus indicating 1 or more steps, okay. The language of the grammar is defined by L of G is equal to W such that S derives W in 1 or more steps. That is what this plus basically indicates. Let us look at this grammar we just now saw. E produces E plus E, E produces E star E, E produces parenthesis E close parenthesis. I have also added one more here, E produces minus E, negating the value of E. E produces ID. Now what I say? E derives minus E. E is my start symbol. I can actually derive anything from this E, okay. I am substituting minus E here. This E I have substituted with ID. So this is one possible string, okay. This string belongs to the grammar. If I apply a rightmost derivation, I have E plus E producing E plus replacing the rightmost non-terminal first, okay, E plus ID, which in turn derives ID plus ID. Or alternately, E derives E, which in turn derives ID star ID plus ID. That is, I can substitute this E with E star E and then substituting the last E with E plus E, and then finally replacing all the E's with ID. That will result in ID star ID plus ID. So this is one derivation. So I can show this derivation as a process by indicating a implies symbol, or I can construct a derivation tree, okay. So that is what basically this derivation process does. Now the parsers. So with this in mind, we have context free grammar available for all the programming constructs, be it a declaration statement, be it an assignment statement, be it an expression, be it computation involving arrays or pointers or whatever it is. You have context free grammar defined for all your programming constructs. Now all strings that are part of the programming language will be definitely based on this particular construct, okay. So therefore parsers are designed keeping in mind the context free grammar, and this context free grammar is basically used for designing your top down parser or your bottom up parser. Now let us just look at a hierarchy of grammar classes. We have here LR of 0 grammar first. Now this LR stands for left, input is scanned from left to right, and this R stands for rightmost derivation. And SLR, under LR of 0 you have SLR, you have LA LR1, you have LR1 and finally LR of K. All these LR are bottom up parsers. Now on to LL, you have LL of 0, LL of 1 etc. up to LL of K, and all these are top down parsers basically, okay. LL indicates it is a left, input is scanned from left to right. The next L indicates the derivation is going to be a leftmost derivation. Leftmost derivation basically goes from top to bottom, so we use that in top down parsing. and rightmost derivation basically happens in bottom up parsing. So, we go from bottom to top. Now, this is what we just now talked about, left to right, leftmost derivation and k tokens look ahead. That is, you will remember how many tokens will occur later. So, you will design your algorithm based on keeping in mind k tokens could follow this particular current token. Okay. LR of k again similarly left to right input is scanned, rightmost derivation and k tokens look ahead. SLR is a simple LR, it uses follow sets basically, it uses the follow, which we will talk about it later. LALR is a variation of LR which is called as look ahead LR. Okay. Now, LL methods basically uses left to right and leftmost derivation and recursive descent parsing. Okay. Now, LL parsers cannot handle left recursive grammar, or it cannot handle if the grammar has got a left factor problem. Okay. Therefore, left recursion has to be eliminated from a grammar, as well as the grammar has to be left factored. Okay. Now, consider this grammar. Formally, a grammar is left recursive if there exists a non-terminal A belonging to non-terminal set such that there exists a derivation of the form A derives A alpha for some string alpha belonging to non-terminal union terminal plus. Now, whatever it is, this is the formal definition as per the textbook. So, you should have A produces A alpha, that is the LHS non-terminal should basically be the same as the first symbol on the RHS production. It could be a direct production available or it could be a derivation. Okay. So, you could derive this in 1 or 2 steps, that is a possibility, or you can have a direct production itself as available. This has to basically be removed. Okay. Now, these are problems. So, if I have A produces A alpha or beta or gamma. Now, A alpha, this is going to be a left recursive grammar. Beta and gamma are non-left recursive productions. This is a left recursive production. Now, when will I say a grammar has left factor problem? Okay. When a non-terminal has 2 or more productions whose right hand side start with the same grammar symbol, the grammar is said to have left factor property. Example, A produces alpha beta 1 or alpha beta 2 etc. up to alpha beta n or gamma. That is, for all these productions other than gamma, alpha is your prefix. So, when you are trying to parse a particular string, until you see beta or until you go until alpha, you will not know whether I will encounter a beta 1 or a beta 2 or beta 3 etc. up to beta n. So, therefore, you may have to backtrack a long way up, okay, and then start applying an alternate production. So, therefore, this alpha is same for all these productions. So, this has to basically be removed. That is why we call it as left factor. Now, the problem with left recursion is it becomes a left heavy grammar as against right heavy grammar. Again, the same issue what I just now said with reference to left factoring. That is, when I have A alpha 1 or A alpha 2, till I see alpha 1 or alpha 2, I do not know whether I have to substitute with A alpha 1 or A alpha 2. So, therefore, we have to remove left recursion and we have to left factor a particular grammar. Now, the order of that is you have to first remove left recursion and then check the modified grammar. If it has got left factor problem, then you remove it, else you can go ahead with the processing of constructing the parsing table. So, that is the first 2 steps. These are the 2 prerequisites. First is left recursion elimination, next one is left factoring the grammar. So, the first thing is eliminating left recursion. Okay. So, this is the algorithm for eliminating left recursion. Arrange the non-terminals in some order A1, A2 etc. up to An, and for I is equal to 1 to n, do for j is equal to 1 to n I minus 1, do replace Ai produces Aj gamma with Ai produces delta 1 gamma or delta 2 gamma etc. up to delta k gamma, where Aj produces delta 1 or delta 2 or etc. up to delta k. That is, you are trying to replace this Aj with its productions, okay, rather than having it as directly Ai to Aj gamma. Okay. So, rather than only one production and then Aj having some k productions, you are converting Ai itself to have some k productions. Then eliminate the immediate left recursion in Ai. So, this is how you basically do. So, you rearrange your productions first and then you eliminate your left recursion. So, how do I eliminate the left recursion? For example, if I have A produces A alpha or beta or gamma or A delta. So, I have two A productions, I have two non-A productions. For every A production, try to introduce a new non-terminal. Okay? Try to introduce a new non-terminal. I am calling that as AR here. Okay? Try to introduce a new non-terminal. I am calling this as AR because it becomes a right heavy grammar. Therefore, I am calling that as AR. So, what happens is this beta and gamma will have the last component as AR, okay, and where I had A alpha or A gamma, make this AR produce alpha AR and gamma AR or epsilon, add one more epsilon. So, where I had two productions here beta or gamma, these two will have a suffix as the new non-terminal, and this new non-terminal will produce alpha delta with AR as its suffix. So, it will produce alpha AR or delta AR. So, beta or gamma that retain as it is by adding AR at the end. Similarly, where I had A alpha or A gamma, add AR and AR at the end of alpha and delta, and then also add one more production called as AR produces epsilon. Let us take this grammar. A produces BC or A, B produces CA or AB, and C produces AB or CC or A. Now, there is no direct left recursion as you could see, but definitely there is an indirect left recursion. Okay. So, what will I do? I is equal to 1, nothing to do because your loop starts from j is equal to 1 to I minus 1. So, when I is equal to 2, you add j is equal to 1. When I is equal to 2, you add j is equal to 1. Okay. J starts at 1 and then stops there. So, what will I do? B produces CA or AB are the two productions here. B produces CA or AB are the two productions here. So, I have to substitute for this A from here. Okay. That is what I am doing here. This A is replaced with BC as well as with this A. So, I am getting 3 productions for B as against 2 productions for B. Okay. And so, that becomes CA, BCB or AB, and now I have to remove the immediate left recursion. So, immediate left recursion is BC is my immediate left recursion. I am introducing a new non-terminal BR, and BR produces what is it? Alpha followed by BBR, okay. Alpha is CB here, alpha followed by BR or epsilon, and this B produces CABR or ABBR, okay. So, these two are the CA and this AB are the two non-left recursive productions, and this is a left recursive production. So, this is how I basically remove it. Then going on to the next one, I equal to 3 and j equal to 1, C produces AB or CC. Now, for A, substitute as BC as well as for A, okay. And then I am getting here two productions, there is no immediate left recursion. Now, I equal to 3 and j equal to 2, substitute for this B with CA, okay, and then this is already existing, etc. So, this B has got now multiple productions. So, all these are substituted here, and then now I have productions for C. Now, C has got CABRCB or ABBRCB or AB or CC or A. Now, this one and this one are the two left recursive productions of C, and the other 3 are the non-left recursive productions of C. Now, I introduce a new non-terminal here CR, okay. CR will now have alpha followed by CR, okay, alpha 2 followed by CR or epsilon, and C will produce beta BR, beta 2 CR as well as beta 3 CR. So, this is going to be your situation. Now, let us take this expression grammar. For example, E produces E plus T or T produces, this is your expression grammar. Okay. Now, this grammar has got, this is a left recursion, this is a non-left recursion, this is a left recursion, there is a non-left recursion, there is only immediate left recursions, there is no indirect left recursion for this particular grammar. So, here what happens, E will produce E plus T. So, I have to introduce one new non-terminal here, I am calling that non-terminal as E dash, okay. So, I am calling this non-terminal as E dash, correspondingly I am calling a non-terminal called as T dash for T star T, and there is nothing for F. So, here E produces T E dash and E dash produces the residue plus T E dash or epsilon. and here similarly T produces F T dash and T dash produces star F T dash or epsilon, and F produces parenthesis E close parenthesis or ID, that remains as it is. Only for E and T, these two has got A productions, therefore I get rid of it, I eliminate left recursion by introducing two non-terminals E dash and T dash correspondingly for E and T respectively. So, just summarize this particular module where we have looked at the properties of top down parser and bottom up parser. We looked at how it basically goes through, and we have also looked at the first pre-processing of this top down parser, which is nothing but removing of left recursion. Okay. Thank you.